Morning, guys and girls. Hope everybody's doing well. Today, I'd like to push on into a little bit more information about acids, right? We should wrap up the last of information about acids today, setting us up to finish out some discussion on bases at the end of the week. So, quick recap of what we've learned so far. We learned that acids have certain properties, right? That they taste sour, they make indicator paper red. If they put them with a metal, it's going to release hydrogen gas because of the single replacement reaction. And if you put an acid with a base, it's always going to give you an ionic compound, a salt, and water. Some acids conduct electric currents. We're going to dive into that a little bit deeper today. Which ones conduct, which ones don't, and why. So we went through our different types of acids. We said there was this thing called an Irenaeus acid, and it was the most specific definition to meet, the hardest to meet, because it had to make a specific ion, the H3O plus ion on the right side of the equation. Right? So you only get to be an Irenaeus acid if you see this ion on the right side of the arrow, and that means one of the two over here is the Irenaeus acid. So how do we figure out which one it is? Well, that ties into the second type of acid, which is called a Bronsted acid. And more generically, we've figured out that acids are proton donors. They like to give away hydrogens, or they allow their hydrogen to be taken. So what will happen is you get an acid like hydrogen chloride, hydrochloric acid, and a highly electronegative element comes over, wants to form a force with this H. The H leaves and the electrons stay, and that's what makes HCl an acid. It donates its H to that water, and because it creates the hydronium ion, it is also an Irenaeus acid. And we looked at a few examples of those. And then last we said Lewis acid is the least specific, and it is simply an electron pair acceptor, right? So anything that produces H3O plus, if it's Irenaeus, is automatically a Bronsted and a Lewis. Anything that is a Bronsted acid, a proton donor, is automatically a Lewis acid. So as long as you can spot your proton donor, it's very easy to identify acids, because if you see the proton donor, you know it's a Bronsted, you immediately know it's a Lewis, and then you just check, oh, do I see H3O plus on the right side of the equation? If you do, you say, hey, it's also a Irenaeus acid. So I said that we wanted to get into this idea of conducting electricity. Why can acids conduct? Because we know things that conduct have ions in solution. Right? And that has to do with something called acid dissociation or acid breakdown. Right? So there's two ways that we depict this. The top one is we say we have HA, some generic acid. All acids have hydrogen. And A just stands for anion, some negatively charged species that's with the acid. So in this slide right here up top, it's just showing you that this is breaking apart into H plus and A negative. I always like the bottom depiction better, because we are saying that an acid is a proton donor. Well, here it doesn't look like it's giving it away. It looks like it's just falling apart. In reality, your acid sees water and it gives the hydrogen to water, creating the A negative ion, leaving it behind, and H3O plus, and a proton and a hydrated proton, hydronium, are the same thing. It's just a proton with with water attached, and it's a proton without water attached. And since most of these are happening in aqueous solution, there's always plenty of water to be had. And so here's our acid dissociation equation. And who this acid is, the identity of the A negative, is going to control how it breaks down. Right? So the strength of the acid is dependent upon who the acid is. Right? So by definition, acid strength is defined by the amount of hydronium ions it places into solution. We've done that equation. You've got your reactants, you've created your products. If I am a strong acid, we break down 100%. Every single acid molecule donates an H to water, and we have all ions at the end. 100% hydronium and A negative. So strong acids do this 100%. How do we know who our strong acids are? Right, there is a list of strong acids that I have you guys learn. 3 come from the periodic table, and 3 are polyatomic ions. Right, so the 3 from the periodic table all live in group 17, HBr, HI, and HCl. And then your 3 polyions are HNO3, HClO4, and H2SO4. So if I were to put hydrobromic acid into water, you would say it breaks down 100%. Hydroiodic acid, 100%. Hydrochloric acid, 100%. Nitric acid, 100%. Perchloric acid, 100%. And sulfuric acid, 100%. And you're going to find out even a bit more because it has 2 H's, and we'll talk about it. If I am not on this list, if I'm not one of these 6, I am a weak acid. I break down 5%. So a very easy question could be, I would say something like, talk to me about how a particular acid breaks down. I could say, well, what if we had HF? I could say, is that strong or weak? And what percent does it break down? So if you look, HF is not on the list. So if it's not on the list, we know it's a weak acid. If it's a weak acid, it only breaks down 5%. So if I were to put 100 HF molecules into water, I would get 95 HFs that remain connected because they don't dissociate, and I would get 5 that break down. So I would get 5 H3O pluses, and I would get 5 F negatives. So 95 stay together, and the 5 HFs that break up give me my 5 of each of the other 2. If I gave you something like HNO2, you would look, HNO2, ooh, close, but not on the list. So it's not on the list, same thing. It is weak. It breaks down roughly 5%. If I gave you something like HBr, you would look, HBr is on the list. It's a strong. It breaks down 100%. So if I just change this F to a Br, everything's different. I would have 0 HBRs together at the end, and I would get 100 H3O pluses and 100 Br negatives. And the ones that give you 100% dissociation conduct electricity really well because there's lots and lots of ions floating in that beaker, lots of H pluses and Br negatives. So it would really conduct. In the weak acids, since most of them are stuck together and they don't have very many charges, they only conduct a little bit. And that's where we're going to go from here. So we now know who is strong and who is weak. And we talked about how they break down. So if we're looking at a strong acid, they dissociate completely. So if this is HCl, HBr, HI, and the 3 polyions, you get 100% HA, H plus, and A negative. If we have a weak acid, It's anything that's not on the list of 6 that starts with hydrogen. At the end of the dissociation, they're still almost entirely HA, and you get a very tiny bit of H plus and A negative. Right? So that's how we can tell if they'll conduct or not. That's how we can tell if they are strong or not. So there's some terminology that comes up that tends to confuse people. When I say an acid is strong, people tend to assume, oh, that acid is strong. It's really dangerous. And that's not true. Strong and weak is what we just talked about. How much do they break down into ions? Safe and dangerous has to do with how potent the solution is, right? Just like salt water, right? I could make varying degrees of salt water solutions. One that you don't even taste the salt. I sprinkle just a little bit into water. And one that's so salty you want to spit it out, right? And that doesn't affect the strength of the salt. It affects the molarity of the salt, or the molality, or the percent mass, the concentration. So what makes acids dangerous is how much of it is present to react with your skin, for instance. So I could have a strong acid that has such a low molarity that it is perfectly harmless to me. But I could have a weak acid, something that breaks down 5%, that is so potent with its molarity, it is very dangerous to me. So this slide here is trying to talk you through that. The term strong means it breaks down 100%. The term weak means it breaks down 5%. If that is all I know, each of those acids may be dangerous or safe. I do not know enough without a molarity to say if it's safe or dangerous. The terms that describe the safety are the two over here. We have dilute and concentrated. Dilute acids have small numbers for their molarity. That means that they are safe. Doesn't matter if they're strong or weak. If it's dilute, it is safe. Concentrated means they have a high number for their molarity. That means they are dangerous. Again, does not matter if they're strong or weak. So what we can do is make sure we understand that idea. If I give you a couple of different acids, we should be able to talk about their strength and their safety. So if I said you have 14 molar hydrochloric acid, the formula part tells you strong or weak. It's as simple as, is it on the list of 6? The numeric part for molarity, molality, or percent mass tells me if it is concentrated or dilute. So as we look at this first one, 14 molar, that is a high molarity, all right? And generally we think anything above 1 is pretty strong in terms of potency. All right, so 14 molar would be concentrated. HCl is on our list of 6, so it is strong. So this is strong because it's HCl, and it's dangerous because it's 14 molar. If I were to make this be 0.004 molar HBr, I look at this, the number part tells me that this is dilute because it's a small number for the molarity. HBr is on our list of 6, So it is strong. So when people ask me, oh, Mr. V, what's the strongest acid you have? I think what they're always really asking me is, what's the most dangerous acid you have in the chem lab? Right? So my strongest acid is sulfuric acid in the back, right? Because it is on my list of 6 and it has 2 H's it can donate. So it puts the most ions in solution. But my most dangerous acid in the chem lab, right, is I have 18 molar hydrochloric acid in the back. Right? And the 18 molar is the highest molarity acid I have. It is also strong, right? But I have 12 molar acetic acid in the back, and that's a high molarity of a weak acid. It is still plenty dangerous. So let me show you one of those, and then we can move on. Right? So I could have something that is 12 molar, and then acetic acid is hydrogen acetate, HC2H3O2. So again, the number tells me concentrated or dilute. The 12 is a big number. It's concentrated. It is dangerous. The formula tells me weak or strong. HC2H3O2 is not on my list of 6, so it is weak. That tells me simply it breaks down 5%. It won't conduct electricity well. So there's a big fundamental difference between the concentration of an acid and the strength of the acid. The concentration tells me about safety. It's the molarity. The strength of the acid is the list of 6. It tells me about the percent that it breaks down. So a few times as we've gone through, I have mentioned that my sulfuric acid is special because it's the only strong acid on the list of 6 that has 2 hydrogens. It has multiple hydrogens. And they give those a name. When you have the ability to donate more than 1 proton, right, you are known as being polyprotic. So poly, many, protic, protoned acids. So many protoned acids. Here's the thing. When they donate those H's, they donate them 1 at a time. So if I'm looking at this acid here, which is oxalic acid, and that's just the polyion you don't know, when I get the H2CO3, don't think of it, H2C2O4 rather, don't think of it as it's bursting apart into its ions, where it's like, oh, I get 2 H pluses and I get the C2O4 -2, right? Remember, they're donating these hydrogens to water, and they can only do that 1 at a time, right? So if we look at this guy over here, the HC2H3O2 I was going to try to copy and paste that over, but the HC2H3O2, HC2O4 rather, gives its first H away to a water, making that H3O plus, and it leaves behind HC2O4 negative. There's still an H remaining after it gives away its first one. And that ion is then able to give a second H to a different water, creating the C2O4 -2. So it happens in 2 separate steps. So H2SO4 is tricky. People think, oh, the H2SO4 is going to give twice as many H's as the rest of the strong acids, but it doesn't, because watch. Right? The H2SO4 sees a water, gives its first H to the water, and we get H3O plus, and we get HSO4 negative. Because H2SO4 is strong, this happens to the tune of 100%. Every single H2SO4 gives an H2O water, and we get H3O plus and HSO4 negative. That leaves behind the HSO4 negative to see another water. It will give its H away, H3O plus, and it leaves behind the SO4 negative 2. But because this guy is not on our list of 6, he's weak, which means this extra H that gets donated only happens to 5%. So it doesn't give away double the amount of the other strong acids. It gives away 100% plus the additional 5%, because the thing that's left behind is not a strong acid. All right, so sometimes they'll ask you what the overall process for this looks like, and then all you do is cancel stuff that you see on opposite sides of the equation that are the same. Those guys would go, and then add together stuff on the same side that you see. So if I wanted to draw an overall process for this, I'd say I have H2SO4 with 2 H2Os creating 2 H3O plus and an SO4 negative 2. And that's what the overall process would look like there in the red. All right, and then the last thing I want to talk about on this is the names of these things. All right, I always add this to this slide, right, when we have it in class. So if you can give one hydrogen away, you are known as monoprotic. So HCl is a monoprotic acid. If you can give 2 H's away, you are known as diprotic. Something like H2CO2, carbonic acid. If you can give 3 H's away, no shock here, you are triprotic. And a good example of a triprotic acid would be H3PO4. And then anything more than 3, they just generically call polyprotic. Right? But those acids tend to be pretty few and far between that are big enough and strong enough and stable enough to possess 4 different H's all in different spots that are donatable. Right? But 1 H is monoprotic, 2 H's is diprotic, and 3 H's is triprotic. Right, so as you can see, that sets us up to talk about bases tomorrow to finish out the week. Coming your way in a parent square is this video, right, where we walk through this, and page 462, numbers 1 through 4 are all questions related to strength and type and dissociation of acids. 1 o'clock today, I will be available for questions, right, in the Google Meet. All right, now send a reminder of that as well. Hope everybody's doing well, and I look forward to seeing people soon.